You're listening to Climate Champions, a podcast from the Architects Journal. I'm Hattie Hartman, Sustainability Editor at the Architects Journal. In this episode, we continue our focus on building performance, exploring how one of the UK's top practices tackles the performance gap, including a revealing post-occupancy study of a Stirling Prize-winning school, which found that the school's heating demand was almost 10 times the predicted load. We'll learn why.
And I'm Hattie's co-host George Morgan, Director of 1.5 Architecture.
Why are we an industry spending this amount of money on buildings without actually checking if they work properly? Why is that not happening? We do analysis. If an architect comes to us with the germ of an architectural idea, we can then take that thinking, apply performance parameters to give them some geometric outputs, which they can then develop into an architecture for a building. And we're doing that on solar gains, energy, comfort, ventilation, embodied carbon. As part of that, we try and do some post-occupancy evaluation of every building that we finish.
Today, our guest is Craig Robertson, Head of Sustainability at AHMM, the fourth largest practice in the UK, according to last year's AJ100 survey, currently with about 500 employees. Craig took up his post in 2014 after completing his PhD at the UCL Energy Institute, where his research focused on how energy can inform both strategic and detailed design decisions. Craig's research was way ahead of the curve then. By now, many clients and most architects are asking themselves this question, or at least they should be. I first met Craig after he started at AHMM when we shared a panel discussion at the Bristol Architecture Centre on what was then a niche topic, energy literacy for architects. This is still too much of a niche topic, but becoming less so every day. Craig's current research focuses on the relationships between architecture, performance, place, and investment, and he now heads a team at AHMM. He's going to talk to us about how the delivery of sustainable design has evolved over the years at the practice. And then we're going to dive into a recent building performance study of AHMM's Stirling Prize-winning Burntwood School in southwest London, completed in 2014. Building performance studies of high-profile award-winning buildings with the findings shared in the public domain remain extremely rare, especially when they flag up a significant performance gap. In the case of Burntwood School, heating loads were 9 times the design prediction, while electricity loads were 4 times as much. Shocking as this may sound, it is not unusual, and Craig is going to explain why and what we need to do about it. A key premise of the study was to investigate the relationship between energy performance and indoor environmental quality. You can't look at energy in isolation. This conversation reveals in practice the many building performance issues we discussed in our last episode with Judith Kempion when talking about our book, Energy, People, Buildings. Craig, it's great to have you on the podcast today. Before we talk about Burntwood School, I want to ask you some general questions about how your team works across the practice to embed sustainable design in projects. Before you joined, AHMM had commissioned Michael Pollan of Exploration Architecture to develop this approach on a consultancy basis. Can you describe for us the trajectory of the delivery of sustainable design at AHMM from when you first joined until today?
Hi, Hattie, and thanks very much for having me. I joined, as you said, AHMM 8 years ago, and at the time we were using Michael Pollan on a consultancy basis to administer what we call the AHMM Sustainability Toolkit. So he would come in and do design reviews, design workshops with project teams at periodic stages throughout a project's design life in the practice to advise on strategy and detailed design moves that we could make to improve the sustainability at the time of our buildings. So I joined in 2014 when a decision was taken to bring that in-house. The kind of incumbent head of sustainability decided to move into project work. So they brought in me as a sustainability specialist at the time, carrying out design workshops, doing some modelling of buildings, albeit without decent software at the time. We're trying to introduce some kind of performance aspects into our building thinking. At the time, I was also teaching on UCL's MSc in Environmental Design and Engineering. So once a week, I was tutoring on a couple of modules which were about low energy designs for specific building types, which was theatres and natural ventilation. So using kind of building fabric as the driver of low energy architecture. So every week I was going away and seeing these dynamic iterative design process using modelling software and having this really kind of excited conversation about the architectural moves and the physics of that and what it meant for the building and the energy consumption. So trying to bring that back to AHMM and trying to introduce that design rigor and iterative thinking around energy and indoor environmental quality into our buildings. Over time, we improved our software that we were using. So we brought in IES, which is a absolute dog of a bit of software to use, but very powerful in terms of its analytical outputs. So we brought that in and started analysing some of the buildings, so the more prominent buildings we had, so we could begin to inform early stage architectural decisions. And then our team grew. We brought in our first employee, so it was two of us then doing some modelling. So I was able to do some strategic work, advisory things, and then we had somebody modelling, developing tools, and sort of beginning to inform things. I should also say that whilst I'm the head of sustainability, we've called the team the building performance team. My thinking was that sustainability is quite an abstract term. Building performance means something. It's about the architectural decisions and how they influence performance, particularly around energy, but also around occupant satisfaction, indoor environment, and all that kind of stuff. So over time, our team has expanded into, there's now 5 of us, and we've been trying to recruit for the last year, which we find really difficult. But there's 5 of us. There should be 7 or 8 of us. And we do analysis. We've developed parametric tools to inform if an architect comes to us with a kind of the germ of an architectural idea, we can then take that thinking, apply performance parameters to give them some geometric outputs, which they can then develop into an architecture for a building. And we're doing that on solar gains, energy, comfort, ventilation, embodied carbon. We have our tool for embodied carbon, but we can build it into lots of our design processes. And because we're working as a kind of in-house consultancy, we're really responsive to AHMM's workflow. As part of that, we try and do some post-occupancy evaluation of every building that we finish. Obviously over the last 2 years through lockdowns and stuff, we just haven't been able to get into buildings at all. And even if we have been able to get into them, there's been nobody in them to inform an evaluation. But sometimes it's just a walk around a building with the FM team and talking to a few occupants. Sometimes we get in and monitor and do bus surveys and various things. So we try and do a bit of that, but we need to do more of it.
Most of this was resourced by the practice rather than by a client?
Yep, almost entirely resourced by the practice. So I'm lucky enough to be in a position where our team is an overhead, in the same way that our model shop is an overhead. We make lots of physical models as part of our design process. The practice of taking the decision that energy modelling and performance modelling is equally important to developing our designs, and that's something worth paying for. If we do some post-occupancy evaluation, we'll take a fee for that. Sometimes because there's specific costs and risks associated with it. But the internal work is generally as an overhead.
Is that post-occupancy evaluation on residential projects as well as non-resi ones?
We try to do everything. Residential is more difficult to get into just because of the multiple people you have to talk to. But as it happens this morning, I was just putting together a proposal for a large-scale post-occupancy evaluation on one of our projects in South London. Our client has monitored the building. We're working with another sustainability consultant who's going to lead the overall reporting. We're going to do the bus survey and the occupant satisfaction stuff. So hopefully it's going to start in May.
Are there other work streams within your team besides post-occupancy, the building performance one?
Yeah, so we've got a knowledge transfer partnership with UCL at the moment. We're 18 months into a 2-year research project funded by us and Innovate UK, and that is looking at zero carbon buildings, the opportunities and constraints with large scale mixed use, urban, commercially driven, complex buildings. And we're using one of our projects, our large South London £300 million mixed use residential, commercial, leisure building as a case study for that. We're about to publish some papers and some sort of guidance documents out of that imminently, which I think is really exciting. And then towards the end of this year, we'll publish a couple of tools that we've developed on the back of that research to help others benefit from the learning we've got out of that.
What does zero carbon mean with that? What are the boundaries of what's counted?
Good question. You will need to wait to read our. Our boundaries are A to C in Rick's terms, plus D, plus offsets. That's what we've called zero carbon. I mean, I have problems with offsets being counted in that, absolutely, because it's fudgeable and mutable and not guaranteed, but we've taken it as the full life cycle. So what we're trying to do is stimulate better design. If we take into account A, that's upfront carbon, so driving that down as close as we can with our design. B is important because AHMM have got a history of designing buildings that can flex and change over time. So what we want to look at in that is how our architectural decisions can eliminate or minimize embodied carbon and operational carbon throughout the life of a building, resource use, waste, through clever design. So we're including that in our definition specifically because we can analyze the implications of our architectural decisions on that in-use phase in both operations and embodied. Then C, how we take a building apart. We hope we don't have to take a building apart, but it might be that we design a building so that the frame can last forever, but we can take components of it off. So we want to provoke our architects to think about that. And then offsets, we include specifically to make the point that this is not a good thing to have to count. So we want to minimize everything before we have to go to offsets.
So tell us about the study that you've recently undertaken at Burntwood School, which recently won the Sibsey Barker Silver Medal. These types of studies are still much too infrequent. What prompted it and who funded it?
So this study was carried out largely, almost entirely by UCL, by Nishesh Jain, who was the lead author of the paper. We were approached by UCL initially to get involved in a project called TOP, the total performance of low carbon buildings in China and the UK. So they were doing a comparative study between 8 UK schools and 8 Chinese schools. So we put Burntwood forward to be part of that. From that, Nishesh Jain, who was part of that research team, he's also gone on to write TM54, the updated TM54 and things. But through the TOP project, Burntwood was identified as an interesting case study for further study. So Nishesh took it on to do a kind of more detailed post-occupancy evaluation of it. That's what prompted it, and that's who funded it.
Great. So can you explain the scope of the study and its main findings?
Yeah. So the main question was, at the time, and arguably now, the legislative framework. So Burntwood was finished in 2014. It was a sort of sequential construction process.
Because the school is a campus with many different buildings, and the school had to keep on operating throughout construction.
Yeah, exactly. So it was designed a long time ago is the point. And at that time, the legislative framework had an energy focus, an operational energy focus, arguably still does, although perhaps we're moving to more progressive metrics. So the argument was that if you design buildings focused purely on operational energy using limited calculation methodologies such as Part L, you're going to miss a whole load of stuff and indoor environmental quality might suffer because of it. So it was to investigate that as a premise. I should say that our client and the head teacher, they were really into the idea of going and seeing how it worked afterwards. So they were
That's
extremely
brilliant.
supportive of it. Yeah, so the scope was to look at the energy consumption, look at and then monitor indoor environmental quality, including lighting, air quality, VOCs, acoustics, and then talk to staff and flush out any issues that they identified.
So one of the issues for indoor air quality comes from the materials in the space. One of the ways of addressing this is the red list in the Living Building Challenge, which screens out materials with formaldehyde and various other things. What do you think of this as an approach to move forward with in terms of materials and air quality?
So I have to admit, when you sent your notes, I had to look up the Living Building Challenge red list, which I think is great. I mean, we've worked with clients in the past who've had their own lists and their own kind of healthy building materials. Obviously, if we're working with WELL, there's material requirements within that. Our own material library in that database, we try and record on a traffic light system healthiness of materials, and obviously through EPDs and things, we try and assess this stuff. The Living Building Challenge red list looks like a good one to me. I mean, I think I'm kind of agnostic about which list I use.
So how did actual energy loads stack up against the predicted?
So at Burntwood, the paper that we published, it was much higher, right? And actually, I should say the predicted was a Part L calculation.
It would be good if you would explain for our listeners why the Part L calculation misses. It doesn't predict accurately actual use.
Over the 4 years of this research project, we managed to drive down both gas and electricity use to much lower, but it was initially 9 times and 3 times higher, 4 times higher.
I've heard a lot of stats about the performance gap over the years, but 9 times higher is really a lot. And I think it's important to say here that kudos are due both to your client and to AHMM for being willing to share these findings so that we can increase industry understanding about what causes this mismatch between prediction and performance and why it's so widespread across the industry.
So part of the study was trying to understand why, and one of the outcomes of this study is recommendations for that legislative framework. So the Part L calculation is just regulated energy by its nature. It's a building regulation, so it's regulated energy. So it misses out plug loads, server rooms, and a few other quite intensive energy uses.
I'd like to just clarify for any listeners who may not be familiar with the difference between regulated and unregulated energy. Regulated energy is typically all the fixed systems in a building, such as the MEP and the lighting, but it does not include anything that is added by occupants and plugged in, including things like server rooms and catering equipment, which can have enormous loads.
For school buildings, Part L calculation makes assumptions about building usage. So it says kids are in there from 9 till 4, Monday to Friday, 30 weeks a year, term time, and that's it. Part L makes assumptions about the services, how efficient they are, about the fabric, and blah, blah. So what we found through the study was a big chunk of the uplift is non-regulated energy. We also saw that through the study, the school was being extensively used after hours and at weekends and for holiday clubs. So there's a whole load of use in the building that just wasn't accounted for in the original calculation, because by its nature, Part L is a generalized calculation. We also found maintenance and operational things like faulty controls. The team did a flux measure of the fabric of the building. Burntwood was built by precast concrete panels, pre-insulated, so factory manufactured, which we think of as being higher quality because it's factory controlled settings and things. The panels that they measured, the thermal performance was about 3 times worse than we thought it would be. So we're leaking more conductive heat through the fabric than we thought we would. So the combination of calculation methodology, greater use, faulty stuff, miscontrols, no maintenance, and construction quality accounts for the performance gap in this case, which is not unusual.
So how far were you able to drive it down over the 4 years of this study?
So we took 25% off the gas. The electricity stayed broadly the same, actually. So the electricity is plug loads, and obviously over that time, computer use is increasing and mechanical ventilation is increasing. So we took about 25% off the gas. So we're still higher than the Part L calculation by a long way, but hopefully closer to something which is more efficient. But higher than LETI, higher than RBA figures by a long way.
And how did you get around the liability issues that post-occupancy studies often reveal? I mean, it sounds like you had a cooperative client in this case.
Yeah, well, I mean, I think the performance issues on this, there's sort of process stuff. So it's building regulations, and then it's how you put stuff together. And one of the interesting things that came out of this paper was to say that actually to overcome these problems, we need better calculation methodologies at the first place, so we're predicting operational energy more effectively at the first. And as I said, Nishesh has gone on to write TM54, the update of that, which is the gold standard for predicting energy consumption at design stage. But then we need a much more collaborative design team working together to think about this stuff. The kind of zero carbon work we've been doing on lots of our projects has meant that design teams have been forced to collaborate and work more closely together at much earlier stages. What this piece of research identified through work that started 7 years ago is that that's exactly what we should be doing. So even a study which is not looking at zero carbon, it's just a more holistic look at performance in buildings, points to exactly the same thing that we're thinking about now, which is more collaboration, more iterative design work, more performance modeling of building. So it's all pointing in the same direction, which is really heartening, actually.
You don't have any service engineers in-house, do you? You don't have any M&E?
No, we don't have M&E, but we have architectural engineers in our team. So people who've got dual RIBA or CIBSE qualifications. So we have people who can size ducts, but we don't do it. We just know about it so we can better interrogate our design team collaborators.
Right. Were there lessons regarding procurement as well, considering the issues about the construction quality? Does procurement need to change?
Yeah, and I should be careful about construction quality. So we haven't investigated that further. So, I mean, that was just a flux test across a couple of panels. For all we know, the rest could be good, or it could have been a faulty reading or whatever. So I want to be careful about saying that there was a quality issue on that building. But certainly procurement and commissioning, we need to be, it's QA, isn't it? It's quality assurance of what we're building on site, to making sure it's delivering what we think it's delivering. And that requires better on-site quality measures, better checks, better commissioning, better aftercare. Yeah, yes, is the short answer.
What sort of feedback did you get on indoor environmental quality?
So they monitored CO2 levels, VOCs, particulate matters, acoustics, and light levels. The school's partially mechanically ventilated, partially naturally ventilated. CO2 levels were generally good. There's a couple of areas where it was not good, but they identified the faulty fan equipment that was causing that and rectified it through the study, and that was good. Particulate matter, because there's a mechanical ventilation, the school is a campus, it's all off from the main road. So combination of distance from busy roads, mechanical ventilation filtering, PM 2.5 and PM 10 were all good. But what was interesting around VOCs, so while the stuff that we expect to come off furniture and fittings and adhesive and stuff was low and within lower than health levels, it was benzene and another external pollutant, predominantly from traffic, that you can't filter out, that we were getting into the classrooms. So it's a lesson around, even when you're away from the busy road, London air quality means that there's still stuff in the air that we need to be cognizant of and try to design out. Despite that, the air quality was good in the school. The interesting thing around acoustics was from an architectural point of view. So we'd exposed a lot of thermal mass, lots of concrete everywhere to do some night cooling for us. The temperature readouts in hot weeks showed the night cooling that we designed into the strategy wasn't quite as effective. We were just getting a build-up of temperature. So we were able to rectify that through the study and implement more effective night cooling. And in classrooms and hall spaces, we had acoustic baffles in there to dampen down the bounciness. But in breakout areas, so the school has got double and treble height breakout areas at end of corridors and in mid corridors, which are open to staircases, and with hundreds of students moving around, they were quite bouncy, particularly in the breakout areas when you're trying to kind of have smaller tutor groups. We found that they were difficult to hear each other in, so the sort of rectification was to go and add some absorbent material into those spaces. So generally the indoor environmental quality was good. The main drivers of indoor environmental quality were technical issues, as the maintenance of the equipment and identifying those faults, external air quality, and then the energy strategy, as in exposing concrete, was contrary to an acoustic strategy. But because the focus was on energy, not necessarily acoustics, it doesn't necessarily get thought about at design stage. So the initial question of that energy focus of the legislative framework versus a kind of more holistic qualitative focus was borne out by that study.
Did the study explore the effectiveness of the self-shading facades? You touched on temperature.
Yes, sort of. I mean, temperatures were generally pretty good. We didn't look at solar gains specifically, but during design, they were designed to, as you say, there are deep reveals around the windows, and there were positions to deal with solar gains. So the temperatures were generally pretty good inside the buildings, apart from, say, on that hot week, we got temperatures continually rising because the thermal mass wasn't being flushed properly overnight. So you're just accumulating heat in the concrete, which was getting re-radiated into the space. But the temperatures, the comfort temperatures were good. And I think because the comfort temperatures were good, the speculation about the thermal quality of the fabric means actually we're putting more energy in to maintain comfort temperatures in the heating season. So it's a kind of heating season temperature thing, which had impact on energy rather than a solar gain thing in summer having impact on temperature.
That's interesting. So once you've digested all of this feedback, is there anything you would have done differently in hindsight?
Well, I think a more holistic energy model, and we'd do what we're doing now. So there's no embodied carbon study done in the building, for example, because embodied carbon wasn't an issue 10 years ago. We do a whole life carbon assessment with a good energy model. The school also has a biomass boiler in it. which was to give theoretical carbon savings via the Part L calculation. The biomass boiler, like hundreds of biomass boilers across the country, has never been turned on. So the carbon savings that are supposed to come from that pellet-driven system are never realised. So it would be an all-electric building now from renewable sources. But it's a good building. I mean, it's a great building. It's a great school, and it's a great piece of architecture. It's the processes, which is what we would change, which I think, as you said earlier, we've moved on leaps and bounds in generally.
If better modelling is key to closing the performance gap, you've mentioned TM54. How does that compare to Passive House as a way of modelling?
So TM54 compensates for the limitations of Part L by counting everything. So you're not just counting regulated energy, you're counting unregulated energy, and you're also trying to take into account a better idea of actual usage patterns and actual likely occupation patterns. So you can build up a better picture of how the building's actually going to be used. Passive House planning package, I'm not an expert on this, is a building physics package, which does take into account all of these things. But I think what PHPP has over TM54 is that PHPP directly leads into a kind of quality assurance piece on the construction site. So you've got to deliver that airtightness, you've got to deliver that thermal performance. The Passive House certification process comes with an inbuilt quality assurance piece on the construction site, which TM54 doesn't necessarily do. It's just a modelling, it's a design stage modelling thing.
I have another Passive House question. Often practices send people for Passive House training as a way of upskilling. It sounds like AHMM is not doing that. What are you doing?
So we've got a couple of Passive House certified people in-house, and one of our building performance team is going in May on a Passive House course to bring that expertise in. Our first Passive House project just got planning permission recently, so we've been trying for years to deliver Passive House projects. We've been trying for so long that the people who we have previously sent on Passive House courses certification has lapsed because we haven't managed to deliver one in the meantime. So we've now got a large student resi Passive House project in South London, a large affordable housing scheme also in South London as Passive House, and we've got a couple in North London where we're scoping out the possibility for Passive House. So we do have that expertise in-house. Again, we use it as a kind of internal resource to inform our early stage decisions so that when we talk with our kind of external Passive House consultants, we're presenting something to them that is plausible and grounded in what needs to happen.
So having enough understanding to make good early stage decisions and having fruitful conversations with them, but not necessarily spend all the time doing all of the inputting of the data.
So that prompts another question. How do you address upskilling generally across the practice?
Every month, the building performance team has a CPD session, a kind of lunchtime session where we tell people about stuff we have been doing or can do for people. We've made lots of tools, so often those sessions are about showing architects how they can take the tools we've made in our team and use them on their projects. We are using the RIBA's recent CPD core competencies, so the climate competencies, and that we are framing our CPDs around that so that we can make sure we're covering the different aspects that people are expected to do, which I think is, some of them are quite involved. So we're trying to pick that up. One thing we're thinking about at the moment is giving our architects the opportunity to be seconded into the building performance team. So we get resource and architectural expertise in our team. And then at the end of a secondment, they go back into their team and into the wider practice with new skills and knowledge from the building performance team. So we're kind of slowly infiltrating good carbon thinking throughout the practice.
I want to zoom out now and ask more of a big picture question. Do you think our IBA and LETI targets are enough to reach net zero, to reach our targets?
I was involved in writing the RIBA targets, but what we did with the RIBA Sustainable Futures Group, we kind of worked building up, and then LETI worked top down to develop those targets. So having not been involved in the overall carbon numbers, I'm taking on trust that if we build everything to those figures, we're going to get there. And what I'm concentrating on is working to get our buildings down to those numbers. And I think they're hard to get down to, particularly in, as I said, large scale, complicated urban buildings. They're really, really tough. If they're not enough, we just have to stop building stuff. We just have to stop doing things. That's not an architectural problem. That's a kind of societal one. That's a kind of global economy problem.
Because there's always retrofit as a way of addressing the amount we've built. How do you think we should incentivise retrofit?
VAT cuts. That's the kind of first thing, isn't it? We do a lot of retrofit. We're working on a project at the moment, which is early stage embodied carbon evaluations we're doing, we're looking at the implications of keeping the building, adapting the building, demolishing the building, and trying to push clients, sort of showing them this carbon graph and showing them what the implications of doing this are from a carbon point of view. I think the issue often is the values that our clients need to get out of sites, just the capacity for an existing building to take extra floors. So we're driven by an economic decision, which has nothing to do with us, to not retrofit or to do something else. I think there's this sort of the cult of the new sometimes. People just like shiny new stuff.
So I was actually recording as a guest on the Lundown podcast earlier today, and one of the questions concerned your project at Angel Square over the Angel Underground Station. This involves the redesign of Rock Townsend's 1980s postmodern extravaganza, retaining the structural frame only. Interestingly, the 20th Century Society has opposed the AHMM scheme. Can the proposed approach be justified in terms of embodied carbon? Have you had a chance to look at that project in detail?
So that project, we've done lots of work on the embodied carbon and the proposed extensions to it, looking at CLT for the upper floors and various low embodied carbon measures. And as you say, we're retaining the frame of that building. The aspiration is also to solve lots of the programmatic and ground level interface issues at that site. I suppose more generally on projects like that. So we've been working on that building. We're retaining a frame. We're comparing it to LETI embodied carbon design targets. And one of your earlier questions was about, are the RIBA LETI targets enough? If we assume they are enough, then that gives us a really clear carbon budget. For a building like that, where we're retaining a frame, that gives us a carbon saving in the most carbon intensive piece of it. Obviously, it's above a tube station, therefore there's no basement being dug there. So meeting the LETI targets for embodied carbon, which we think are compatible with a zero carbon future, should be enough. And other projects where we are digging a basement, for example, and we're working within the same carbon budgets, that means the frame has to work much harder, or the facade has to work much harder in terms of its low embodied carbon. So I think the conversation around this has become a little bit binary, as these things tend to be, in that, if some things are good, some things are bad. But what we've taken as an approach is that the LETI targets, the upfront targets, or the RIBA A to C targets, is compatible with a zero carbon future, and therefore we try and work our buildings into that number. So, for example, the RIBA 2030 challenge numbers we try and work with. So an A rating on there is, on the LETI scale, is 530, but the RIBA number is 750 kilograms of CO2 per metre squared, A to C. And if we can get all of the components of a building into that number, then that's surely compatible with our carbon future. Obviously, the best carbon building to build is not building a building at all, or keeping the building. But we have to take these targets, these are ambitious targets that we set ourselves as an industry, as a viable carbon budget, and work within them. What that then opens up is the need for really robust calculation methodologies, understanding exactly what's happening on site, so we're capturing all the complexities of embodied carbon. It needs the supply chain to massively decarbonise, because what we're learning, applying these really ambitious metrics to our buildings, all of our buildings, is really difficult. And until the supply chain decarbonises, until the grid decarbonises, until we get a proper handle on the resources actually used to build a building, it's really difficult to get a robust number out of this. We're about to publish a paper from our KTP about the embodied carbon performance gap, which is exactly the same issue with operational energy. At design stage, we're counting up numbers and we're thinking we're getting to embodied carbon of X. Even as we go through the design process and the data source changes, from volumetric model to cost plan, from ICE database to EPD, we're finding the embodied carbon numbers are jumping enormously. I happened to visit a couple of building sites last week, and actually just walking around them and seeing all of the waste, the offcuts, the extra fixings, the trimmers, all the complexity and the kind of messiness of a building site. There's a huge amount of embodied carbon which I think is not captured in our industry's design models. So the robustness of those methodologies, combined with robustness in the actual targets themselves, LETI and RBA targets, if they are viable zero carbon targets, then we should be able to work within them and develop an architecture which works within that, which can be anything, but it's got to be within that target.
So, yeah, in the architecture profession, we focus about buildings and the impacts of the buildings themselves, but there's also transport and infrastructure implications for net zero. So yeah, do we need to focus on including those more in our thinking?
Yes, but again, often those decisions are out of our hands as we get presented with the site. I suppose as part of our zero carbon project, we're thinking about those externalities. We're thinking about the hinterland carbon, lifestyle carbon, I've heard others refer to it as. And I suppose as architects in our building designs, we can make it easier for people to reduce that external carbon by making it easier to cycle places, making it easier to walk, making it more pleasant, all that kind of stuff.
I think I mentioned this kind of toolkit, we call it, which looks at sustainability from 12 points of view. Obviously, carbon is the pressing issue, and we're currently overshooting our carbon targets, so that is where we're focusing a lot of our effort at the moment. But if we are working within a carbon budget and we think those numbers are a kind of viable number to develop buildings within, then that gives us an opportunity to solve lots of the other kind of problems of buildings. So there might be social, townscape issues in housing estates, for example. They could be better in terms of layout for play, for safety, for social size. In terms of biodiversity, we occasionally work with an ecologist who is a consultant to the practice. So she is on hand to give us advice and understand how we can best embed ecological aspects into our buildings. I think the adoption of the urban greening factor by the GLA has been really positive. So we've got a number of kind of guidance documents on that we've penned in-house to help our architects build that into the early stage of their design process and get the kind of areas required. And as I say, with an ecologist's support, we can ensure we've got the substrates and the depths of soils and various things. We've just updated our material library, the database for our material library, and digitised it. So we've got several thousand material samples in our practice, all fastidiously catalogued by our material librarian, and we have upgraded our library database. And in that, we're capturing links to EPDs. We've got a kind of traffic light system on health of materials, VOC content, etc. So through that, we're hoping that architects, when specifying materials and looking for samples, can find healthy ones and low carbon ones and whatever metric they want to use. But we're reliant on the supply chain having that data. We're reliant on the supply chain providing robust information about that and making it readily available. We've tried to capture EPDs in a kind of our own database, but it's a full-time job just to keep that going. So we're reliant on our manufacturers having decent links from their information, or NBS specification software is beginning to give us that information so we can capture healthy materials. But I think it's a really exciting time because all of this stuff, carbon, healthy materials, we're at a point where the kind of whole industry, the whole supply chain seems to be realising that this is complex and difficult and needs much better joined up thinking, and we're kind of slowly getting there, I think.
If you could implement one policy change that would make a difference in all this, what would it be?
I've got a really small one and a really big one. Can I have two?
Yeah.
The really small one is I would make some kind of rule that meant energy meters were installed properly in buildings. Every building we go to do some post-occupancy evaluation on, there's something up with the meters and we can't get data out of there, so we can't understand how the building is working. So I'd implement decent metering, monitoring of buildings, every building.
We absolutely need that. That seems relatively straightforward.
And then my kind of more macro scale one would be, I think we do need to think about how the economy works. The economy is driving much of what we're doing, and we're driven to it by the need for ever more stuff. So I think I might try and have a crack at unraveling some of that.
And finally, last question. I'd like to ask you a little bit more about your own journey. What prompted the return to academia and the pursuit of the PhD? And how has that shaped your approach to practice?
So I was working as an architect in the 2000s. At the time, I felt that you're kind of intuitively doing things that you think are better environmentally, but I felt I didn't have the language or the knowledge to be able to express why I thought they were better. So I did a part-time MSc in environmental design engineering whilst working as an architect to try and equip myself with the knowledge and the expertise to better express myself as an architect when talking about environmental issues in architecture. That so happened to coincide with the financial crash, and simultaneously, after my MSc, I was offered a PhD. I went and did a PhD at the Energy Institute, and that was, as you said earlier, looking at how we could use energy, using a database of energy consumption, design and actual data, what that could tell us about the design process, construction process, and ultimately management of buildings. And at the time, there was very little people getting decent data out of buildings. So it was an exploration about why are we in industry spending this amount of money on buildings without actually checking if they work properly? Why is that not happening? What came out of that was a sort of guide to how we could work practice better. So actually, I think coming to AHMM and having the freedom to build a team and make things happen, I'm sort of implementing the recommendations at the back of that bit of research in terms of how we should work together, how we should evaluate buildings at design stage, how we should understand what's happening in them afterwards, so we can bring that knowledge back into the early stage of other projects. So retrospectively, I think it's sort of it's been massively informed how I've approached my role at AHMM and what we've been doing, and the focus on performance, the teaching roles that came from that PhD, and how the students were kind of invigorated by an iterative performance-based design process coming out of that bit of research is exactly how I've approached it at AHMM.
Well, that's a great place to stop. Thank you for sharing this Burntwood study with us. I think we really need to get these messages out across the industry. It is starting to come through in certain schools in curriculum, the importance of building performance, but not many. And it is still slow to catch on in practice. So thank you very, very much, Craig. Great to talk to you.
Thanks very much for having me. Cheers.
Our next guest will be architect John Christophers, talking about what he's learned about building performance from his own home, a fossil fuel-free domestic retrofit in Birmingham completed in 2010. John tweets at @ZeroCarbonHouse. If you're enjoying Climate Champions, please rate us and subscribe on your favorite podcast platform. It helps people find us so we can build an audience. You can find the show notes for this and previous episodes at architectsjournal.co.uk/podcasts. Thanks for listening.